Hey everyone, I'm Gwen from Nile, and today I want to talk to you about using JSON data in Postgres. So we're going to start with why would you want to use JSON data in your nice relational database. Then we're going to spend a bunch of time just at how you do it, creating tables, creating indexes, querying, what's efficient, what's less efficient. We'll cover all that. Obviously, we'll talk about how to use JSON in Nile's virtual tenant databases. If you are using Nile and you're so inclined, finish with how do JSONs actually get stored in Postgres. And I have a hint for you.
Cut it, cure it, toast it.
There you go. There you go.
Okay, why store JSON in Postgres? Postgres is a relational database. You have rows, the rows have columns, the columns have data types. When you insert, these data types are validated, so it gives you a lot of safety. You have all those nice relations, foreign keys. Why would you want to use it for JSON? The main reason you want to use JSON in your pristine relational database is that A, you actually like having a relational database, you enjoy the structure when it makes sense, and you also enjoy things like transactions, ACID, all those things that we associate with using Postgres. However, a small subset of your data does not fit this model very well. As an example, if you also use your Postgres to store authentication data and you authenticate by integrating with a bunch of authentication providers like GitHub and Google and maybe WordPress, all those, when a user uses them to authenticate, it gives you access to their user profile. But the user profile is different for each provider. If you use Google, you probably get an email address. If you use GitHub, you may get some repositories. If you use WordPress, you probably get a blog address. So you have some data that is in common, but then a lot of the data, just different fields per provider. And it can even be that the same information is in fields that have different names. So this is unstructured data. Now, I doubt you want to throw away your entire relational database and move to MongoDB just because you need to store user profiles. So this is a good case. Each user has some fields that are in common, like the username and maybe a pointer to credentials. But then you have a JSON with all the other fields in the profile, which would be different depending on what the user filled in and where did it came from and all those things. So that's one use case. The other use case that I ran into that is fairly common, if you use Postgres as a vector store, then you want to store metadata for every one of the chunks that you have embedded. That can also be very different depending on what is the source of the embedding. If you embedded pages out of a PDF, you may have a page number. If it's from a blog post, you probably do not have a page number. So you can see how this would be different depending on the document type. It can be different for each tenant. Some tenants may give you more data for their documents. Some other tenants would give you less data. So now you understand how it's useful. Let's take a look at how to do it. I'm obviously going to use my Nile database, and we're going to start with, surprise, surprise, creating a table to store our JSONs in. Now, this is a tenant-aware table, so I'm going to store JSON for different tenants. You can see that I'm not using JSON column, even though it exists. I'm using JSONB. And you should also use JSONB. I cannot think of a lot of cases where there is a downside to using it. What does JSONB mean? It means that Postgres takes your JSON and stores it as binary. There is also some operations that Postgres supports for JSONB and does not support without JSONB. This is the containment operator. I'll get to it in a second. So don't pessimize your tables and just default to storing everything in JSONB. Okay, and we have our table. What do we do now with the table? Obviously, we need to store some data. So let's insert a product or two. So you can see here that we have the product is a smartphone, and product details is a great place for use of JSON because the details will be different for each product. Sure, things like brand maybe and price are probably in common, but then iPhones have colors. It's not just a model. So you may need in some products to have a color field, in others not. If you have products that can come in different quantities, you probably need a quantity field in some product, some you may not need it. So you can see how you'd have different fields, which is very convenient instead of making this table super wide with every possible field, and then it will be very sparse because most products do not have every possible field. You just create a JSON with all those details and trust Postgres to store it and query it efficiently. So let's insert that. Fantastic. Now that we have stored some data, the next step is to query it, right? So there is a bunch of different ways to query your JSON data. I'll go over the common. Let's start with a simple query. So over here, we are filtering by tenant and by the name of the product. And instead of getting all the details, we only want one detail. We only want the brand. This arrow operator means go into the JSON and give me the value of the key brand. Now this is without a column name. It's usually cleaner to have a column name. So let's add that. And you can see that the brand is XYZ. Now, if you remember the JSONs that we previously used, it was a very simple JSON. So let's select with this JSON. You can see that it has 3 keys. 2 have string value, 1 has integer value. The arrow operator here brings you back the value in object format. Now here the object is text, so it doesn't matter. If you have nested JSONs, then it does matter that you get back the value in object format, because then if you can actually access some sub-details. So if the brand had, let's say, brand names, you could actually continue and say, I want the name out of it. This is going to return an error because brand is a text and obviously it does not have fields. But you can see how it goes. Now we also have a double arrow operator. This returns the value in form of text. So if you have nested JSON, you basically get the value as a text format JSON. In this case, it will make absolutely no difference because it was text anyway. Okay, so now we know how to get specific fields out of a JSON call, and also how to drill down in case you have a nested JSON. And you know about the arrow and the double arrow operator and can use them accordingly. Another very important operator is the containment operator, which is how you filter based on data in the JSON. So you say, I want all the JSONs that contain a specific key and a value. And this searches for JSON objects that contain this as a sub-object. So if we run it, we'll get basically the exact same thing because we only have one row. So this containment operator, it's only supported by JSONB. So this is one good reason to use JSONB. And you can optimize it even further. If you have a lot of JSONs of all kinds of different structures, you can also create a containment index. Now, before we talk about indexes, you may ask yourself, why do we need a containment operator and check for containment where we could also do something that looks a lot simpler, like this? This will return the exact same results, but there are good reasons to use containment versus convert to text and then do text comparison. First is that JSON gives you a lot of flexibility. It is an object, it has multiple fields. Doing containment basically asks, is this object contained in the other object? So it's a form of object comparison, which gives you a lot of flexibility around partial matches, nested structures that basically you cannot really do efficiently with text. Like imagining I want the brand to be this, and then this other nested object also has those other fields. So nested comparisons and flexible comparisons is a big reason. Leveraging the indexes that we'll soon talk about is another good reason. So you could use both if you just want to compare a single text field one against the other. Both are valid. Containment gives you flexibility for more complex matches and is more optimized and uses those indexes. JSON indexes are all GIN indexes, which is kind of a more generalized type of index than the usual bit trees. And you can create an index on the details column using GIN. Then if you run the exact same containment query that we had before, it will just be faster because now, in this case, it's one row, so it's not going to be any faster. But if you had substantial amount of data there and then some subset of your products had the brand key and they had this particular brand, then using the index would obviously speed things up. One other thing you can do is to aggregate data. So now I want to count how many products I have from each brand. So I can run this query. It's basically group by and convert the brand to text. So it ends up being a normal group by operation on a text column. So we extract the text out of the JSON. If you have something in the JSON, some text in the JSON, and you want to perform a text search on your JSON data, then you can also do that. So here we are filtering by the tenant, and then we're converting the description text to a vector, and we use text query to search for those two words in the text. So running this, we don't have any fast processors. So sorry about that. You may have to search in a different store. So let's update our JSON and add a description. Okay, so over here I'm deciding to update the details for a product, and I am setting the JSON to a different JSON. And you can see that I use JSON set. I can give it the column as the source and then tell it add a new object to it called description, and this is the description, and I'm casting the string to also be JSONB. And then obviously I'm making sure that I'm using the workflows to filter by tenant and smartphone to make sure I'm updating the right data. And we successfully updated a row. Now let's try the search again. Great. Now if a customer looks for fast processor, you can see that our A100 is really fast. So we've covered few common JSON operators. We've covered arrow, which lets you access a value in a JSON and return it as an object, so you can continue drilling down into additional sub-values in nested JSONs. We also learned about the double arrow, which returns a value as a string, which is useful if you have nothing to drill down any further. We learned about the containment operator, which lets you search that the JSON includes a specific key and a specific value, or several of them. Just make sure that this object is included as a subset in this other object. And we learned about JSONB set, which lets you update the JSON, either add a new key or update the value of an existing key. There is also a bunch of other operators. You can delete keys, you can concatenate, you can expand the JSON into arrays of columns, you can do all kinds of interesting things. Now, one thing that I promised to you is to discuss how JSONs get stored. Let's take a look at how the columns in our table. So I'm going to do this query, and I'm going to filter Okay, so I'm going to take table products and look at all the columns and how they're stored. You can see that my product has several columns, and if we look at how they're stored, you can see that 2 of them have plain storage, and then the other 2 are marked with an X. This is extended storage, not to be confused with external storage, which I'll get to in a second. JSON and text are stored as extended, while the integer and UUID are stored as plain. So what does extended storage mean? Let's go back to how data is stored in Postgres. That in Postgres is stored in pages. Those are Postgres pages, not to be confused with your operating system pages, which are slightly different. Postgres pages are always 8 kilobytes in size, and Postgres wants to store rows in these pages. So every time I insert a row into a table, it is stored in a page, and they're trying to make it consecutive. So all the rows from a table will be stored one after another in the same page, and you have 8K for it. So this can be thousands of values if all you store is a couple of integers, or if you store very large text or JSON, it can take the entire 8K, it can take more than 8. What does Postgres do? Everything over 2K is already considered large, and Postgres will store it in an external table that stores just overflow chunks that did not fit into the page in the original table. This is called toast. The tables that store all those extra chunks are called toast tables. So anything over 2K will get chunked up into 2K chunks and sent and get stored in a toast table. The original table will point, hey, the data is actually there, which means that querying toast by definition is a bit slower, because you have to jump through the hoop of I'm looking here and then I'm looking there. So you may ask yourself, why is Postgres not missing this data? And the answer is that it actually is compressing the data. So if you see external storage X, it's not only toasted, it is also compressed. The other type of external storage, I said that we have extended and external. So extended gets toasted into a different table and it gets compressed. But what if you have data that is actually already compressed? You don't want Postgres to spend CPU cycles compressing it. We also have external storage, which is for data that you are planning not to compress. So if you are uploading, let's say, JPEGs, you probably don't want to compress JPEGs. It's already a compressed format. You store it as is. Let me try to show it to you. Okay, so here I'm storing an embedding. You can see the embedding has an E next to it. Why is that? Because my embeddings are dense vectors. Dense vectors do not compress very well. They are essentially already a compressed representation of a chunk of text, and therefore we store them in extended, which is in external, which is exactly like extended but not compressed. I always have to reference because it's easy to mix things up. So one thing to keep in mind about toast is that if you actually store small values, they may get stored inline. The fact that the storage that we have external or extended attribute means that it's toastable. It could, if there is large data, store it in toast. It means that the first few bytes of the data that is stored there is used to say if the data is indeed in this column is indeed toasted or not. But if your data is not that big, it will actually not get toasted. So you can actually go and check if the JSON data that we inserted, was it toasted or not. So let's take a look. And over here with this query, we are basically checking which tables also have a matching toast table. And it looks like we are not using toast at all, because our JSON was very small, and I'm guessing that either I did not insert any vectors or they are pretty small as well. So we did not actually toast any of our data. We have only created a column that is toastable. If we had a very large JSON that would take more than 2 kilobytes, then it would get toasted and a toast table would be generated. Okay, so that's it. You've learned why you want to use JSON in Postgres. You learned that you should use JSONB rather than JSON for optimization. You learned some of the common ways to query your JSON and how to use indexes to speed your JSON queries up. Then we talked a bit about how JSON is stored, and if it's very large, it may get spilled into a toast table, which has some over. So that's it. If you have built your multi-tenant application and you use JSON data in cool ways, definitely let us know. Ping us on our Discord or on social media, and we'd love to hear about what you built. And if you haven't yet built multi-tenant application, whether or not it uses JSON, if you want to build one, obviously you're welcome to use Nile and enjoy our tenant awareness and tenant virtualization with or without JSON data. So happy hacking.